Hi, folks. In this lecture, we're going to search for truth. Well, okay, at least our scientific version of it. So let's begin again by looking at the fundamental kernel of scientific information called the measurement.
A measurement has two important pieces. One of the parts of the measurement is the unit, which dictates the type, standard, and scale of the measurement, which we discussed in the lecture about measurements and base units previously. The piece of the measurement we're looking at in this lecture is the number which tells us how many units are being used in the measurement and contains the vital information of how precise the measurement was conducted. For us to accept the measurement as truth, we also assume the measurement was conducted utilizing a rigorous procedure to minimize human and instrumental error, which, as skeptical scientists, is a huge assumption. Let's say we read that there are 0.052 milligrams of chromium in every liter of the water coming out of an industrial plant near our town. As a knowledgeable scientist and citizen, we are presented with a piece of data, whether it be in a science journal or in the local newspaper. But we have to ask questions about that number before we can accept it as truth. In this lecture, we're going to be looking carefully at the steps involved in a rigorous measurement procedure that's designed to answer the most critical questions surrounding measurements. There is a fundamental fact about measurements that we always need to be aware of. There is always error in a scientific measurement. Thus, there is no absolute truth in a measurement. Though we try and try, there is always some random error that can't be fixed. The best we can hope for is a measurement that was conducted with instruments that were appropriate to the scale and property we wanted to measure, that the measurement is accurate with any fixable error being fixed, and that the final value of the measurement represents the precision of the instrument correctly. So let's go back and look at each of the components of the measurement in more detail. We need an example that I can use throughout these next few talks to describe a measurement. I've got one. I'm an avid golfer. Matter of fact, if I weren't stuck here in my studio, I'd be out playing right now. That being said, golf is a pretty good example to describe some of the principles guiding measurements. Well, golf is on my mind all the time anyway, might as well use it. Now, the flag and golf hole out there, we will call truth. Now, we're pretty sure that it exists, and we want to find the truth using our measuring instruments, the golfer and his trusty golf clubs. Let's work through a measurement process and outline the steps required to produce an accurate quantitative measurement. First, we need to choose the appropriate experimental method to use for our measurement. This choice will be based on several factors. We want to pick an instrument that matches the size of what we're measuring. For example, a bathroom scale is pretty good at measuring the weight of a human, but not appropriate for weighing a butterfly. Using my golf analogy, let's say we have a hole about 100 yards away. Using a driver, that would be too much club. I hit that club about 220 to 250 yards, and thus it's a bad choice for finding the golf hole only 100 yards away. A highly lofted iron, such as a 9-iron or pitching wedge, which were designed for shorter length shots, would be better choices. How accurate and precise do we want to be? Accuracy is the measure of how close to truth we are in our measurements, and precision is the measure of the scatter or uncertainty of the measurement. Typically, high degrees of accuracy and precision are equivalent to money. I I can buy a bathroom scale pretty cheap and use it to get a relatively accurate estimate of the weight of a dog. So if I want to weigh one of my corgis, this one is named Riley, by the way, a precision of about a pound or two will probably be all I will get from the bathroom scale. But to get a more accurate and precise weight of the dog, I would need to invest more money in my weighing instrument and maybe even call in specialized technicians to calibrate the instrument so I can be assured of obtaining an extremely accurate and precise result. In the golfing analogy, we have me and my clubs that can hit golf shots to find the truth, or we could hire, at great expense, a finely tuned professional golfer like Tiger Woods or Ricky Fowler, and be assured of a much more accurate and precise measurement. It is also important to realize that a measurement can be very precise, but not necessarily accurate. Looking at the golfing analogy in the diagram, we see a series of golf shots that represent measurements that are very precise with a small amount of scatter, but on average are pretty far to the left of the flag and not very accurate. There is obviously something wrong with the golfer's technique and is evidence of some systematic error that should be fixable. But the precision is great as we see all the balls located in a tight pattern. Then we have a series of measurements that have noticeably more spread and are less precise, but on average are much closer to the truth. Here the error looks random and will be a bit harder to fix, but the accuracy is acceptable. It is, for this reason, we need a rigorous method for alleviating systematic error to assure that we're getting as accurate a measurement as possible, no matter what the device is and how wild its precision. Accuracy is attainable if we fix or account for the systematic error. The precision is what we're paying for when we purchase and use a very nice instrument. So from here on out, we're going to assume we can fix the systematic error in a device. The question we'll need to answer when choosing an instrument is what precision is acceptable to us. Other factors and questions that must be asked in choosing an appropriate experimental method include: how many samples do we want to analyze? How long will it take to do the measurement with this method? How much skill is required to use the method? How complex is the sample? Measuring the weight of a butterfly is a much harder proposition than measuring the weight of a static dog, seeing the butterfly doesn't want to stay on the scale. How many components are in the sample? Measuring the amount of ethanol in its pure state is much easier and can be done cheaper than trying to measure the ethanol content in gasoline, which is a very complex mixture of compounds.
Okay, we're going to stop here, but we'll pick it up again in the next video. There's much more we want to talk about as we get into the details of the measurement process and our quest for scientific truth. See you soon.